liberate man from dogma and deception. I am one small piece of nature.
You have a grandstand seat here to one of the most momentous events in the history of science. In less than a minute, you will see the most powerful explosion ever witnessed by human eyes. The blast will come out of the horizon just about there. And this is the significance of the moment. This is the first full-scale test of a hydrogen device. If the reaction goes, we're in the thermonuclear era. For the sake of all of us, and for the sake of our country, I know that you join me in wishing this expedition well.
It is now 30 seconds to zero time.
Minus 15 seconds. Minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2,
16, some months before the bag was sold, breakfast. We were at the Garris Hostel. He told me, he wrote down the proper pronunciation of his name, which is not Jean, it's Joachim. And he corrected me on something I told him. He's from Munich, outside of Munich. He teaches on the web. And he corrected me about something I told him. I had an inverse square law of gravitation when I was 13 years old, and I discuss it. I said I discuss it only with my closest friend, James Colosimo. He said no. He said no. He said and what he said basically was, you also discuss it with Richard Page. Richard Page is in Memoirs of a Child Prodigy. We did free fall experiments in an elevator in Chicago from the Prudential Building. We did free fall experiments. That's in Memoirs of a Child Prodigy. So apparently from what Joachim said, I also discussed my inverse square law of gravitation at age 13 years old with Richard Page. And his exact words, he said that it's already been checked. He said, it's like the Bible. Like the Bible. I later told this to Aidan Sirkan, and he said, yeah. Okay, so that's what I'll put on there now. And then they can check with Joachim. He told me where he lives about 60 kilometers outside of Munich, and he teaches on the web. Teaches languages. Apparently pretty good.
I am one small piece of nature.
So, Albert Einstein described himself. In 10 years, Einstein went from high school dropout to formulator of the theory of relativity. How? Why? What can we learn from his career about our most precious resource, the human mind? Albert Einstein's discoveries in physics ranged from the molecular to the universal. His formative years, the years of his unequal creativity, were spent here in Switzerland. In his education and his character may be revealed answers to the riddle of all genius. Albert Einstein submitted only 14 lines in response to a biographical request from the PhD. That modest summary conceals one of the greatest adventures in human thought. Despite his renown for making science of our century, remained simple and unassuming in his person. The secret of Einstein's genius may well lie in his simplicity, his childlike curiosity, his complete concentration, his playful visual imagination, and his openness to the symmetry of nature. But there is something else. The human intellect is a delicate flower, said Albert Einstein. His career reveals how we must nurture the mind to help liberate man from dogma and deception. I am one small piece of nature. Einstein went from high school dropout to formulator of the theory of relativity. How? Why? What can we learn from his career about our most precious resource, the human mind? Albert Einstein's discovery
discoveries in physics ranged from the molecular to the universal. His formative years, the years of his unequaled creativity, were spent here in Switzerland. In his education and his character may be revealed answers to the riddle of all genius.
What I'm going to talk about tonight is one of those things. But there's a quote that I like. There's a quote that I like very much. It comes from a famous intellectual by the name of Sherlock Holmes. And it says, when you have eliminated all that is impossible, which, by the way, sometimes takes 5 years, when you have eliminated all that is impossible, whatever remains must be the truth, no matter how improbable. The thing I'm going to tell you tonight is one of those things which seems nutty, it seems wildly improbable, but it wasn't just something that some of us, I wasn't alone in saying this, that some of us just said, oh, one day, oh, you know, maybe the world is a hologram. That's not the way it happened. The way it happened was exactly this way. When you eliminate everything that's impossible, whatever is left over must be the truth. The universe is at least 1,000 times bigger in volume than the horizon region. So there's stuff out there. That stuff is simple. But finally, is our cosmic horizon, the one surrounding us, is it a two-dimensional scrambled hologram of all that lies beyond it? These are questions which are deep, profound questions, and the only thing, I am not going to answer them, the only thing I can say now is we are all wrestling with them, and they're big questions, and they're hard questions. That's the physicist, incidentally. That's the universe. So I hope I've given you some flavor for the kinds of questions which we ask. But I want to convey something to you, that it's an extraordinarily remarkable fact. It's not a fact about me, it's a fact about the way human beings think, the way human beings, their cognitive abilities, that when you think about it for a moment, you know, a small, relatively small band of hairless apes has been able to deduce all of this, has been able to deduce such strange and totally unintuitive, very, very foreign ideas, very, very abstract ideas about the universe as peculiar and as unintuitive as the world is a hologram. I thank you.
Would Albert Einstein plead for a vision that exhibits 1. Childlike curiosity, and 2. Exhibits the symmetry in nature, and 3. Is the culmination of a child's visual thinking, whose audiometric analog is, unequivocally, the prelude to also Sprach Zarathustra, and is in fact the uncontestable physical theory of e pluribus unum? Would Albert Einstein express himself with great passion on the question of the making of a motion picture for children worldwide?
is my great pleasure to welcome you to the second of Lenny Suskind's 3 messenger lectures. Based on the number of people who stepped up to us and introduced themselves to Lenny and tell him how thrilled they are to meet him in person, ignoring me, I think I need an introduction more than he does. So, I'm Paul Ginsberg. I'm a professor of physics and information science here at Cornell. And I'll say a few words about this particular lecture series and then give a short introduction to Lenny. So Cornell's messenger lectures were established in 1924.
Oh, can I ask you to call me by my actual given name, Leonardo?
Leonard Susskind. By a gift from Dr. Hiram de Messenger, Dr. Hiram Messenger, a Cornell graduate of 1880 and a longtime teacher of mathematics. The terms of the original gift established, pay attention, a fund to provide a course of lectures on the evolution of civilization for the special purpose of raising the moral standard of our political, business, and social life. There was a period when anyone who was anyone in the pantheon of physics was a messenger lecturer here, going back to R.A. Millikan, 1925, remember the oil drop. Sir Arthur Eddington, 1933, remember the solar eclipse in 1919. J. Robert Oppenheimer in 1945, well, Fred Hoyle in 1960. Richard Feynman, 50 years ago, 1964, up to including recent messenger lectures in the past decade. Sir Martin Rees, Stephen Weinberg, Nima Arkani Hamed. I was told to ask out of curiosity, how many of you were here for Feynman's lectures 50 years ago? So I count about 10 or 15 people. After the lecture on Monday, I was thrilled to, somebody who was an undergraduate visiting his children here told me the same thing. Now, tonight's speaker, Lenny Susskind, was born in the South Bronx of New York City in 1940, went to City College of New York, came to Cornell in 1962, both to escape taking over his father's plumbing business in the South Bronx and also to receive a PhD in theoretical physics in 1965. He went to Berkeley, was on the faculty of Yeshiva University until 1979. Since then, has been a professor at Stanford, including most recently since 2009, the director of the Stanford Institute for Theoretical Physics. He's one of the founders of string theory, actually the one who introduced the notion that particles could be described by excitation states of a relativistic string. Has 4 decades of over 200 cutting-edge research articles, still growing rapidly. He's one of the, he has various awards, National Academy of Sciences, American Academy of Arts and Sciences. I'll read only his J.J. Saccharine Prize citation for pioneering contributions to hadronic string models, lattice gauge theories, quantum chromodynamics, and dynamical symmetry breaking. His expository gifts have carried over to the popular realm. He's authored a number of popular books on subjects from cosmology to black holes to quantum mechanics. He's been on Nova shows discussing various aspects of physics. Now, the words he uses will also be an incredibly prescient 50 years earlier second lecture, an introduction to tonight's lecture.
Hi. I can see the audience tonight, so I can see also from the side of it, which last time was a black spot in front of my eyes, that there must be many of you here who are not thoroughly familiar with physics. And also a number that are not too versed in mathematics, And I don't doubt that there are some who know neither physics nor mathematics very well. That puts a considerable challenge on a speaker who is going to speak on the relation of physics and mathematics, a challenge which I, however, will not accept.
There in the middle of the screen is Lenny. He says no. Let us welcome Lenny Susskind.
All right, I have a couple of things to say before I start. The first thing I want you to know is that I actually did bring a jacket and tie to Ithaca with me. I'm not wearing it, but I did bring it. You know what? I'll prove it next time. I'll prove it next time. Dick was better dressed than I am. The second thing I wanted to talk about was the way I begin lectures. I often write out a couple of paragraphs, and then I actually read them. Sometimes I don't. And somebody asked me, why do you sometimes do this and why do you sometimes not do it? And the answer is it really does depend on what I had to drink before I lecture. Tonight I had a couple of beers, so I have this terrible fear of completely forgetting what I'm supposed to talk about. And so I write a few paragraphs to get me started. So if you don't mind, I will begin by reading my paragraphs. But even before that, I want to second the thing that Dick said. I actually don't know how to aim a lecture like this. I really don't. I have the feeling that, that my problem is similar to our President Obama's. Anything I say will leave almost everybody dissatisfied. But here goes. Quantum mechanics is confusing. I think we will all agree. Oh, actually, I'm not sure. David Merman probably doesn't agree. He understands it better than we do. But apart from David, yes. It's also true in most other physics that the number of degrees of freedom that it takes to describe a region of space is proportional to its volume. We have found out by the series of indirect arguments that any region of space can be described by a collection of degrees of freedom which are no more numerous than the area of the region in Planck units. That led to a conjecture. It led to a conjecture that any region of space can be described by some kind of theory describing degrees of freedom on the boundary of the region of space. That is what was called the holographic principle. Holographic because it's like a hologram. That was a conjecture. It was a, you might even call it a speculation, which is worse than a conjecture. But it was in 1994 or so that this conjecture was put forward. Most people at the time thought it was a screwball notion. But it took a couple of years, basically until 1998, until a young Argentinian physicist whose name you should know. I ask people, do you know who Juan Maldacena is? I'm talking about physicists or physics groupies and so forth, and often they don't. Juan Maldacena is perhaps the greatest physicist of his generation. I won't tell you how old he is. He's younger than me, so he's not necessarily greater than me, but he is certainly the greatest physicist, greatest theoretical physicist of his generation. I'm going to write his name. Maldacena. Mal stands for bad or something, but I don't know what is this? What does bad of? What is Sena? It's Italian, I think. Bad of Sena. Anyway, his first name is Juan. Juan Maldacena produced a perfectly rigorous description of this for a particular kind of space-time called anti-de Sitter space, but that's not what's important. What's important is he dotted the I's, crossed the T's, and found an extremely precise mathematical description of the degrees of freedom on the boundary which would describe a region of space. And indeed, it turned out that there were no more of them than 1 per Planck area on the region of space. So in some sense, the world is really described by a kind of holographic description on its own surface. Just to make it graphic, everything in this room, there is enough degrees of freedom on the walls of the room to describe everything in the room. It is as if the walls of the room could be thought of as a hologram describing what's happening in the interior. Okay, so we got through the holographic principle. Thank you.
So while you're thinking about questions to ask the lecturer, I have 3 comments. The first is Juan Maldacena will be giving the beta lectures this fall.